and welcome to the next video in this unit on differential equations. In the video on orthogonal polynomials, I told you that we'd learn about where the different weight functions for the different sets of orthogonal polynomials came from. Well, that's what we'll do today. The basis for this is Sturm-Liouville Theory, which is a general theory for second-order ODEs. First, we'll define Sturm-Liouville Theory and explore some of its more important properties. Then we'll look at several different boundary value problems and eventually answer the question, can you hear the shape of a drum? We can write all linear second-order ODEs in Sturm-Liouville form, d by dx of p of x times du by dx plus q of x times u equals minus lambda times w of x times u, with boundary conditions alpha 1 u of a plus alpha 2 u prime of a equals 0, and beta 1 u of b plus beta 2 u prime of b equals 0, where w is the weight function. Here we will consider only regular ODEs, where all of the coefficients p of x, q of x, and w of x are continuous and differentiable on the domain a through b. Imagine we have a general linear second-order ODE of the form p of x times u double prime of x plus q of x times u prime of x plus r of x times u of x equals 0. I said that you can put any linear second-order ODE in Sturm-Liouville form, but it isn't necessarily obvious how we do that. We can do this by multiplying the whole equation through by the integration factor, mu of x equals 1 over p of x times e to the integral of q of x over p of x dx. Then in Sturm-Liouville form, the equation can be written as d by dx of mu of x times p of x times u prime plus mu of x times r of x times u equals 0. Sturm-Liouville equations can be written as eigenvalue equations for the Sturm-Liouville operator. L equals minus 1 over w of x times d by dx of p of x times d by dx plus q of x, given by L of u equals lambda u. The Sturm-Liouville operator is self-adjoint, such that the inner product of LF with G equals the inner product of F with LG, where the inner product is defined as the integral from a to b of f bar of x times g of x times w of x, where f bar of x is the complex conjugate of f of x. Since L is self-adjoint, the eigenfunctions of L form a basis for the Hilbert space of all square integrable functions on the domain a to b, with the inner product we just defined. So this is the key to Sturm-Liouville theory and why it is so powerful. This theory is the foundation of why Fourier series, orthogonal polynomials, and many other functional expansions work to solve differential equations. Much of the theory of special functions comes from the solutions to commonly occurring Sturm-Liouville problems. The Legendre polynomials are solutions to the Legendre differential equation, 1 minus x squared times pn double prime minus 2x times pn prime plus n times n minus 1 times pn equals 0. This equation shows up when evaluating the Laplacian operator in spherical coordinates. In Sturm-Liouville form, we can rewrite this as an eigenvalue problem, d by dx of 1 minus x squared times d by dx of p of x equals minus lambda times p of x, with eigenvalues lambda equals n times n plus 1, and weight function w equals 1. The Legendre polynomials are solutions to this differential equation with boundary conditions pn of 1 equals 1 and pn of minus 1 equals minus 1 to the n. Going back to the Laplacian in spherical coordinates, spherical harmonics are the basis for 3D rotations. Legendre polynomials appear in the polar component of this decomposition, Pn of cosine theta, and correspond to rotations about the z-axis. For example, these are the spherical harmonics for n equals 0, 1, 2, and 3. Another example is the Hermite equation, u double prime minus 2x times u prime plus m times u equals 0, which can be written in Sturm-Liouville form as d by dx of e to the minus x squared times du by dx plus m e to the minus x squared times u equals 0, where the integration factor is the Gaussian e to the minus x squared. This is where we got the weight function w of x equals e to the minus x squared for the inner product for the Hermite polynomials. One particularly useful application of this is inhomogeneous equations. Imagine we have an inhomogeneous linear second-order ODE, L of u equals p of x times u double prime plus q of x times u prime plus r of x times u equals f of x. Because this is a linear equation, superposition holds for all solutions to the homogeneous equation, L of u h equals 0. The most general solution to the inhomogeneous equation is u of x equals a u of x plus up of x, where of x is the solution to the homogeneous problem, and up of x is a particular solution to the inhomogeneous problem. We want to write this in Sturm-Liouville form. L of u equals 1 over w of x times d by dx of p of x times du by dx plus q of x times u of x equals f of x. We can identify the functions p with pw, p prime with qw, and q with rw, which gives us a differential equation for w, given by w prime equals q minus p prime over p times w, which we'll call alpha w. We can solve this by integration. W equals e to the integral of alpha dx. That means that we can solve the original ODE by expanding the function f of x as the sum on I of alpha I times ui of x in the basis of eigenfunctions for L. Because there are an infinite number of distinct real eigenvalues of L, the generalized Fourier series for f converges. Then the particular solution to L of u equals f of x is given by up of x equals the sum on I of alpha I over lambda I times ui of x. One example of this you may have seen in other contexts is the damped-driven harmonic oscillator. X double prime plus 2 beta times x prime plus omega naught squared x equals f of t, where x of t is the position of the oscillator at time t, beta is the damping coefficient, omega naught equals the square root of k over m is the natural frequency of the oscillator, and f of t is the driving function. Let's assume there is no damping for this example, so our Sturm-Liouville operator is L of u equals d squared u by dt squared equals omega naught squared u. This has solutions of the form un of t equals an sine n omega naught t plus bn cosine n omega naught t, where sine lambda t and cosine lambda t are the eigenfunctions of L corresponding to the eigenvalue lambda equals n omega naught. The Fourier series for the driving frequency is f of t equals the sum from n equals 0 to infinity of an sine n omega naught t plus bn cosine n omega naught t, where an equals the inner product of f with sine n omega naught t divided by the norm of sine n omega naught t, and bn equals the inner product of f with cosine n omega naught t divided by the norm of cosine n omega naught t. Sturm-Liouville theory is a key technique for solving separable PDEs. Imagine we have a PDE, a of x times uxx plus b of x times ux plus c of x times u equals ut plus g of t times u, with boundary conditions u of t and a equals u of t and b equals 0, and initial condition u of 0 and x equals f of x. The differential operator for this equation is separable, so we can write the solution u of x and t equals t of t times x of x, and the differential equation can be written as s of t on t equals L of x on x equals lambda, where s equals d by dt plus g of t, and L equals a of x times d squared by dt squared plus b of x times d by dt plus c of x. Here, the eigenvalue equation for the operator L is a Sturm-Liouville problem. L of x equals lambda x, with boundary conditions x of a equals x of b equals 0. This can be solved by the eigenfunctions xn of x for the eigenvalue lambda n, and the eigenvalue equation for s, d by dt of tn equals lambda n minus g of t times tn, can be integrated directly, such that tn of t equals an e to the lambda nt minus the integral from 0 to t of g of tau d tau. So the complete solution for any PDE of this form is u of t and x equals the sum on n of an times xn of x times e to the lambda nt minus the integral from 0 to t g of tau d tau, where an is the inner product of f with xn divided by the norm of xn, where the inner product is defined as the integral from a to b of alpha of x times beta of x times w of x dx, where w of x equals e to the integral of b x prime on a prime dx prime divided by f of x. Imagine we want to solve the wave equation, the Laplacian of u equals a times dt squared u, for a 2D circular membrane of radius a with Dirichlet boundary conditions. We can separate the temporal and spatial components of this equation, u of r theta and t equals rho of r and theta times t of t, so that the Laplacian of rho on rho equals a times t double prime on t equals lambda squared. We have two eigenvalue equations, one for t, where t double prime equals lambda squared on a times t, and the other for the planar Laplacian. The Laplacian of rho equals lambda squared rho. You may recognize this as the Helmholtz equation. Let's look at the spatial component. In polar coordinates, the Laplacian is given by rho r plus rho r on r plus rho theta theta on r squared. We can isolate the r and theta terms by writing rho of r and theta as r of r times theta of theta, so that r squared r double prime plus r prime divided by r plus r squared times lambda squared equals theta double prime on theta equals n squared. The solutions to the eigenvalue problem for theta are theta equals alpha cosine n theta plus beta sine n theta, where n must be an integer, so that theta of theta equals theta of 2 pi plus theta. The equation for r is called the Bessel equation. R squared times r double prime plus r times r prime plus r squared times lambda squared r equals n squared r. Since this is a Sturm-Liouville problem, its eigenfunctions, Jn of lambda r, called Bessel functions, form an orthonormal basis. The boundary conditions require r of a equals 0. Then the eigenvalues are the solution to Jn of lambda a equals 0. There are many places where a Bessel function crosses 0, so we can index the eigenvalue by the mth 0. The eigenvalues are then lambda nm equals jnm on a, where jnm is the mth 0 of the Bessel function jn of r. In the example we just worked out, the circular drum resonates at frequencies corresponding to the eigenvalues lambda nm. In general, we can use the Helmholtz equation, the Laplacian of u minus k squared u equals 0, for an arbitrary drumhead with Dirichlet boundary conditions to work out its spectrum, or the frequencies it will resonate at when struck. These are the eigenvalues k corresponding to the appropriate boundary conditions. For simple drums, for example, rectangular or circular drums, these spectra are different. This raises the question, can you hear the shape of the drum? This is also called the isospectral problem. This question was famously asked in 1966 by Mark Kac in the American Mathematical Monthly, although it had been previously asked by many mathematicians. This question is asking if there are two drumheads with different shapes that have the exact same spectra. It remained an open question until 1992, when Carolyn Gordon, David Webb, and Scott Wolpert constructed two planar regions with different shapes that had identical eigenvalues. Here are two such isospectral drumheads. Thank you for watching, and I'll see you next time.